Let's do a redox reaction together. We have the chromium ion with a -2 charge reacts with an iron ion where it's iron 2, and this becomes the chromium 3 ion and the iron 3 ion. Three of these are very easy. I can see the oxidation state of the iron 2, chromium 3, and iron 3. I need to assign oxidation numbers here for chromium in the dichromate ion. Oxygen is always a -2. I have 7 of them for an overall -14 charge. I know that the overall charge on the ion is -2. So what plus -14 is -2? That must be 12. Since I have 2 chromiums, that means each one of these is 6. Now I need to see what's being reduced and what's being oxidized. My pairs here, iron 2 is becoming iron 3. How does it do that? By losing an electron. And chromium 6 is a +6, becoming chromium 3. How does it do that? By gaining electrons. So my reduction is gain, and so oil rig reduction is gain of electrons. I'm going to start with my Cr2O7 with a -2 charge is going to become the chromium 3 ion by gaining electrons. One chromium has to go from +6 to +3 form. That means it needs 3 electrons. But I have 2 chromiums total, so I need a total of 6 electrons here. And I have to account for my my oxygen. For that, I'm going to make the oxygen be part of a water molecule. I had 7 of them, so if I put a 7 here, that means that I need an acidified solution where I have 14 available hydrogen ions from some acid to react with my oxide ions to form dihydrogen monoxide. So that's my reduction. Let's look at my oxidation. For oxidation, I have my iron 2 becoming iron 3, and in order to do that, it released an electron. Oxidation is loss. Oil rig, oxidation is loss, reduction is gain of electrons. So here we have freed up 1 electron. There are no extra oxygens or hydrogens to be accounted for, so that one's good to go. This as a complete reaction, as a redox reaction, means that I have both the electrons that are being freed in the oxidation are the ones that are being used to reduce something in the reduction. So I need a total of 6 electrons, which means that I need to have this happen 6 times. So I need 6 irons 2s to become 6 iron 3s so that I can have the 6 electrons that I need for my reduction part. So when I write this as a total equation, I would have 14 hydrogen ions, 1 dichromate ion, 6 electrons, and 6 iron 2 ions. Those go to form 2 chromium 3 ions, 7 waters, 6 iron 3s, and freeing up 6 electrons. Looking on both sides, the redundancy is the 6 electrons. So when I write my total balanced equation, I would have 14 hydrogens, 1 dichromate ion. I won't include the electrons anymore. 6 iron 2s become 2 chromium 3s, 7 waters, and 6 iron 3s. A second example might read, the permanganate ion is added to sulfur dioxide in acidic conditions. So let's write the permanganate ion. It has an overall -1 charge. My oxygen's -2 each. There's 4 of them for an overall -8 charge. That must mean my manganese ion is a +7. For sulfur dioxide, oxygen's a -2 for an overall -4 charge. This isn't an ion, but a molecule, so it's neutral. That means my sulfur must be in a +4 state. So I have the permanganate ion reacting with sulfur dioxide, and the permanganate ion is in a +7 form. It is probably going to gain electrons because it's very hard to imagine it even being more positive by losing more electrons. On a list of common oxidizing agents, or things that are about to be reduced, I see that dichromate is the fourth one down here, and in acidic conditions, it's going to go to the iron 3 form. On a list of things that are oxidized or called common reducing agents, third one down are sulfide ions or sulfur dioxide molecules, and they're going to become sulfate ions. So returning to my reaction, my permanganate is going to now be in manganese 2 ion form, and my sulfur dioxide will now be in sulfate form. So I know that here my manganese was +7. It's going to go to +2 by gaining 5 electrons. I have to account for my oxygens here by formation of water, which will require me to have 8 hydrogen ions from my acidic solution. For my oxidation, my oxygen was a +4, but in the sulfate ion, oxygen's a -2. There are 4 of them for an overall -8 charge. The charge on the sulfate ion is -2, so that must mean sulfur has become +6. It was +4, now it's +6. It must do that by freeing up 2 electrons. I needed 5 electrons to run my reduction, and they come from my oxidation. So the least common multiple between 5 and 2 would be 10. So I need to multiply my oxidation by 5 in order to have 10 electrons available, and I need to multiply my reduction by 2 so that it will be consuming 10 electrons. When I write out my whole reaction, my reduction, I now have 2 times 8 is 16 hydrogens, 2 permanganate ions, 10 electrons, forms 2 manganese 2 ions, and 8 waters. In my oxidation, multiplying by 5, the 2 waters are now 10. 5 sulfur dioxides forms 5 sulfate ions. 20 hydrogens have been freed up, and the 10 electrons. Now, this time, I don't just have redundant electrons. I actually have water on both sides and hydrogen ions on both sides. I need to clean up all the species that are found on both sides. And my electrons definitely cancel out, so I'll remove those. Now let's look at, I start with 10 waters on the reactant side and 8 waters on the product side. I'll remove all 8, and I'm left with 2 waters on the reactant side, 2 permanganate ions, 5 sulfate ions. On my product side, I'm left with 2 manganese 2 ions, 5 sulfate ions, and for my hydrogens, I started with 20 produced, and I needed 16 initially. So I am left with an overall balance of 8 on the product side. And that is another example of balancing in acidic conditions.